Hi folks, today I bring you another clock integrated circuit. This time we will be looking at the SC8562, a device that is functionally very similar to the LM8562 from Sanyo. Although these two clock chips are closely related, they contain a few details that can make their reuse a little more challenging. For that reason, we will give special attention to those details throughout this presentation. Let us begin with the power supply connections, because this is one of the areas where mistakes are most likely to happen. I would particularly like to highlight the importance of understanding the meanings of VDD and VSS in this design. In this case, things are not arranged in the way many people might expect. Here, VDD is the negative supply, while VSS is the positive supply. This is an important detail and one that should never be overlooked. We must also pay close attention to the orientation of the diodes and to the polarity of the capacitor shown in the schematic for the SC8562. Interestingly, in the schematic for the LM8562, the capacitor polarity is not indicated. Fortunately, by following the orientation of the diodes, it quickly becomes clear that the VDD is being used as the negative potential. Since this topic has already been covered several times on the channel, we will not spend too much time revisiting it. If you would like a more detailed explanation, I recommend watching some of the previous videos where this subject was explored in greater depth. The display used in this project is based on a duplex LED display. To simplify the assembly process, the display pinout was identified beforehand. One practical difficulty with this integrated circuit is its package. The device uses a 1.78 mm pin spacing, which means it cannot be plugged directly into a standard breadboard. To use it on a breadboard, we need either a pin spacing adapter that converts the package to the standard 2.54 mm spacing, or we need to extend the pins manually, as we have done in previous clock projects that used similar STIP28 packages. The duplex display itself consists of two common cathode displays. The common cathodes are located on the first two pins found on the left side of the display. Immediately after those connections, we find the cathode and the anode of the lower indicator LED, which is completely independent from the main display. Because of this, we must ensure that it also has its own current limiting resistor. Another important detail is that each common cathode should include a resistor of approximately 820 ohms. The final pin on the right side of the display is connected to the center column indicator, the two dots used to separate hours and minutes. The clock and display can be powered using a transformer with two windings of 8.5 volts AC. This works because the operating supply voltage for these integrated circuits can range from approximately -14 volts DC to -8 volts DC. This power supply arrangement has a significant advantage. It avoids the need for a transformer with three separate windings, which can sometimes be difficult to obtain. Once again, I would like to emphasize that the operating voltage is -14 volts DC, not +14 volts. The clock time base is derived directly from the mains frequency. A 100 kΩ resistor is used together with a 10 nanofarad capacitor connected at the input to suppress noise. As you can see, the button interface uses a two-level input system. Because of this design, it is extremely important to include current limiting resistors. Without them, it becomes very easy to create a short circuit when two buttons connected to the same input are pressed simultaneously. The clock adjustment system is also quite interesting. A total of 5 buttons are used. One button is dedicated to entering the clock adjustment mode. 2 buttons provide slow upward and downward adjustment. The remaining 2 buttons provide fast upward and downward adjustment. It is worth noting that the adjustment process is synchronized with the mains sine wave, which is part of the original design philosophy used in these clock circuits. To keep the video from becoming excessively long, I will summarize the remaining features. Like several of the clock chips we have already explored on the channel, this device supports 12-hour operation, 24-hour operation, automatic flashing after a power failure, a sleep timer, and 2 independent alarms. There is, however, one important limitation. This clock does not support 24-hour mode when operating with a 60 Hz time base. That restriction is built into the design of the integrated circuit. After applying the recommendations and observations covered in this video, bringing one of these clocks back to life becomes a relatively straightforward process. Despite a few unusual design choices, the SC8562 remains an interesting and capable clock chip, and it is certainly worth preserving as another example of classic electronic design.